During the first week of May this year, NASA detected 82 significant solar flares originating from two active regions of the sun. These sunspot clusters became highly complex, leading to repeated eruptions throughout the week. On May 7th, several coronal mass ejections left the sun and headed toward Earth, prompting NOAA's Space Weather Prediction Center to do something they hadn't in nearly 2 decades: issue a geomagnetic storm watch for a G4 or greater. As the sun went down that evening, the night sky was filling with displays of the northern lights in areas as far south as Florida. But as social media was lighting up with colorful aurora photos, a massive effort was underway to keep our power on.
We can safely say that the storm in May was the most successfully mitigated extreme space weather storm in history.
Today we're going off the radar to learn about the mitigation efforts that took place during this historic solar storm.
We were constantly engaged with the power grid of North America, and they were sweating it out.
We'll learn about what could have happened that weekend.
Meaning there could have been some bulk transmission failures affecting hundreds of thousands of people.
And what could happen in the future. I've heard some scientists say that we're overdue for that sort of event.
Emily, I think that's fair. I think that's fair to say that we are overdue, because we are.
I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do.
There's more to imagine when you listen, so let your imagination soar with Audible. Audible has audio titles from every genre that will inspire you to imagine new worlds, possibilities, and ways of thinking. As an Audible member, you get to choose one title a month to keep from their entire catalog. Enjoy an exciting reawakening of a beloved classic with the Audible original David Copperfield by Charles Dickens, produced by Academy Award-winning director Sam Mendes, starring Ncuti Gatwa, Helena Bonham Carter, and Theo James. This adaptation breathes new life into a familiar tale. New members can try Audible free for 30 days. Visit audible.com/imagine or text IMAGINE to 500-500. That's audible.com/imagine or text IMAGINE to 500-500.
Garrett Hyde, so glad to have you on the show today. Fellow Sinclair meteorologist, somebody who's gotten a little more familiar with space weather here recently, too. So I want to talk a little bit about that. But you're up there in Cedar Rapids, right?
Yeah, up around eastern Iowa. So yeah, it's a pretty good little area. Every now and again, we get some pretty decent space weather activity, but a little too south sometimes for most of our more predominant shows, that's for sure.
Right. Well, you get plenty of terrestrial weather, too. I mean, I feel like there's always a derecho happening in Iowa.
Yeah, at least a couple a year, for that matter, at least. Yeah, we had like 2 or 3 so far this year already, so it's been a little hectic.
Okay, so you're doing weather there at Iowa News Now, but you're also doing some science reporting. So this story that you did recently about space weather was really interesting to me, and that's why I wanted to pull you on the show here today, because when you think of space weather, you don't often think of some of these impacts that we do see. Impacts to farmers. Can you break this down for me and tell me exactly how space weather can impact farmers?
Yeah, I was originally doing a story with one of the local farmers about how a lot of the excessive rainfall here in Iowa was delaying the planting seasons. The workable field days were dropping down to like 2 days a week, which is not great. So when I went out to interview one of the farmers, he was talking about that a little bit. Of course, that was when we literally I think that Friday before then, was when we had that G5 storm. And then so he was talking a little bit about the fact that, fortunately, I think he just had to switch around some satellite GPS providers, but he had a couple of other farmers that, was in his network that weren't able to plant that weekend, while a lot of those satellites were not connected or not working properly due to the fact that the satellite GPS positioning was having a lot of errors. Due to some pretty interesting processes to what geomagnetic storms can do to our atmosphere.
Yeah, and I guess I was familiar with what they do to satellites. I don't know enough about farming. I didn't realize they were using GPS to that sort of precision and how much it can impact, their business.
Have you ever watched Interstellar?
Yes.
So the very beginning of that movie where, the gravity is throwing everything off and the tractors are completely driving themselves. Like it's kind of like that in a way. They set up the GPS at least to say, hey, these are where my rows need to be. So all they have to do is just get the tractor onto that line, hit go. It takes them down the row. They turn it around, hit go again, and it's just back and forth and back and forth and back and forth. And these GPS precision tractors are actually precise in some cases down to the centimeter. The farmer I talked to, he said normally he switches kind of providers throughout the year, and it can be a couple inches sometimes and that's a more affordable, cheaper GPS provider. But when it comes to planting, harvest season, that stuff gets down to the precision of centimeters, like I said earlier, and it's a big thing. I didn't really realize this is how much 8 inches can truly throw off an entire row of crops and cost thousands of dollars down the road if you mess that up.
Wow. Yeah. Okay. So for this interview, you talked to Sean Dahl. He's a fun guy, isn't he?
Very, very fun person to talk to. I know that was the first time I've interviewed with him, and he's a wealth of knowledge and really, really good person to talk to. That's for sure.
Okay, so your story is online. If we want to see it, we're definitely going to check it out. We're also going to hear a lot from Sean Dahl today. I did this whole episode with him where we just basically start from like the very beginning when it comes to space weather, because it's hard to grasp, it is for me, and I have a science background. So Garrett, thank you so much for your time and for sharing about your story today. And everybody should go check out your piece on farming and space weather. Garrett Hyde, thank you so much.
Thank you very much. I appreciate it.
Sean Dahl from the Space Weather Prediction Center, this area of NOAA that I think people don't even really know exists. We think weather, we think ocean, but NOAA is space weather too, right? So tell me, first of all, because I think most people don't even know what space weather actually means. They're probably picturing like tornadoes in space.
Yeah, of course, Emily. Thanks for having us on your show. It's always great to talk about space weather to the general public, folks like your listening audience, because, hey, it's important. People need to understand it. So what is space weather? Well, it's really what's taking place on the sun 93 million miles away in that huge vacuum of space between the sun and the Earth. And ultimately, what we here at NOAA, the Space Weather Prediction Center, are concerned with is what does that mean at and around here at planet Earth? Because space weather can impact our way of life through the technology primarily that we rely upon so much today.
Yeah, and I'm curious too, because, I think there's so much unknown about space weather, and there's a lot of like rumors that fly around too. So that's a big chunk of why I want to talk to you today, is to clear up some of these misconceptions about space weather. One of the questions I get a lot is, when there's an event that affects Earth, does it affect locally or globally? How does it determine like what it affects? And can just one spot on Earth be impacted but other spots not?
Yeah, Emily, it's strange, right? Space weather in general can be a planetary-wide phenomenon in some cases, like happened back in early May, where you see the aurora globally for such an extensive period of time. But many times something may impact just the sunlit side of our planet, or in some cases more local effects dependent upon geography. The geology that we live upon can impact how some storms react here at Earth and impact certain types of technology, such as our power grid. That's very important. That can be very localized in some cases. And of course, operations in space and the communication methods we're using to go through that atmosphere can be impacted both on the night side or the daylight side, kind of depending on how storms progress. So when we look at space weather as forecasters here at the Prediction Center, we are really focused globally. Kind of a planetary figures are what we're putting out there, because we really don't have the ability yet. You're going to get there, but not yet, to do more localized precision forecasting.
Yeah, I want to make some comparisons and talk about some parallels here with terrestrial weather here on Earth, and how far we've come and the important factors of forecasting weather here on Earth, and those parallels and if they translate into space weather. So we talk about how our observation system has gotten so much better. We have satellites here, we have radar, we have all these initial observations that help us forecast weather on Earth. And then we've got computer models that we put all that information into. So is it the same process when it comes to space weather? Is it this initial observation going into computer models? How do you predict what's coming from the sun?
Yeah, right. It's a bit different yet. We haven't quite gotten there where we have such a wide variety of choices for either observational platforms in space. I mean, we have some, and we have a network of observatories, both radio and optically that look at the sun for us, but nowhere close to what we have in terrestrial weather. Most of us here have meteorology backgrounds, and we did regular weather forecasting throughout most of our careers. So we're quite familiar with how far we've come. Upper air balloon launches across the country, some twice a day, throughout the globe, for that matter, that get ingested into these wonderful models. And there's many different models, so many so that there's ensemble forecasting now, meaning a forecaster can look at a spread of what each model is predicting and then decide based off that spread, where the hurricane may move, for instance. So we've got so much better at that terrestrial weather. In space weather, we're not there yet. As I mentioned, we only have a few platforms or observational systems. They're expensive to get out there because many of these are space-based. And then that alone brings engineering difficulties from time to time on whether they're being tracked and how that's set up, or if we have a dropout of data. Another thing we struggle with is something physical or not physical? Meaning we see sometimes things on these instrumentations that, well, is that the arrival of a storm we're looking for, or is that just a blip, artifact, a problem? And we have to take a little time sometimes to take a look at that. But the art of forecasting for space weather from something 93 million miles away is still very difficult, and it's really about expertise, knowledge about how the sun works, really still quite intuitive with our thinking of comparing activity to activity and events to events and producing regions to producing regions.
So your background is meteorology, right?
Correct. Most of it's meteorology with quite an extensive amount in space weather as well.
Okay, so I'm curious about the people at the Space Weather Prediction Center, and are they meteorologists? And then can you go to school to become a space weather forecaster? Do you get this meteorology education first and then just kind of jump into this field? How does that all work? And how did you learn how to do this, I guess?
Right. Well, it's a very specialized, unique thing, right? Not too many people get to say they're a space weather forecaster in this world. Other countries are doing this now. Most nations have some kind of space weather setup now, and we collaborate with a lot of them. That didn't exist, 2 decades ago. So that's really come around as well now, too. For us here, we have a wide variety of backgrounds. Mine's really through the military. I spent 22 years in the Air Force. I earned a minor small degree in weather technology and applied meteorology, but I have a whole litany of environmental science and physical sciences and more specific geology type classes that allowed me to get what I needed for curriculum requirements for physical sciences. Others have a meteorology degree, atmospheric science. We have a couple of forecasters here that came from National Weather Service regular forecast offices with no background in space weather, but we hired them because of their ability to learn quickly and ability to make quick decisions. Because when you do this work, you have to make quick decisions with very limited information. And as I already alluded to, not even sure if some of it's correct. So it takes kind of a specialized individual that can think that way to put out the products that are necessary and those watches, warnings, alerts that we issue when activity picks up.
So is the backlash over a busted forecast as bad as it is when it comes to working for the National Weather Service?
Right, and it can be. It's not as crucial usually, and in the weather you don't want to mess up a tornado warning, right? Because people's lives are at risk. You got to get that right. And they've gotten much better. We have issuing minutes in advance, compared to after it's already been seen. So that's great. In space weather, we have a little more leeway here. We can protect critical infrastructure that we all rely upon because there's time if things unfold very well, like we see everything, all the engineering's in place, we're getting all the data, something seems very obvious to us, such as the event in May. I'm sure we'll spend time talking about that, how successful that was. But that's that's not the routine or the common. Many times we'll see an event happen in the sun, and we're not even sure if it's facing Earth or if it's going the other direction. That's just the limitation of the instrumentation that we have. So you have to look for other clues to pick up on that. The repercussions, as you allude to, for busting a space weather forecast, since they're usually not going to impact our society in a catastrophic way, it's more minor. But if you don't get it right when there's a big event like a rocket launch that needs to know whether something's an all green or red situation for them, that can mean catastrophic loss of the spacecraft. And we're going back to the moon, so it's going to be critically important for us to get certain aspects right for the health and safety of those 4 human beings on the Artemis Orion missions coming up, later next year.
Mm-hmm. Yeah, and I want to talk about that and the May event too. But I want to go down some of these space weather phenomena because, I think people have trouble telling them apart sometimes too. Okay, so can we go down the list of some of these and you explain exactly what they are to me?
Sure.
Okay, let's start. We all know Aurora Borealis. We all know this is the fun space weather thing. But can you tell me how, the idiot's guide to how these things form, how we see these?
Sure. This forms from the interaction in Earth's atmosphere with the pile of energetic particles, charged particles that are coming from the sun all the time, but even more so during a significant space weather event. Those charged particles get into the outermost layers of our atmosphere, and they interact with the molecules that are up there. And as things settle back down, and this is a continual process, so things fire up, settle down, that emits light. And that's what we see as the northern lights up here in this hemisphere, or what we all call the aurora.
Okay, what is a solar flare?
A solar flare is a blast of energy from the sun. Think of it like a lightning bolt. It's just this burst of energy that covers, differently other than just light, it's spread across much of what we call the electromagnetic spectrum, the spectrum of energy that we all can look at as scientists anyway, at various levels of that. But what we're focused on is the X-ray energy. And the reason we want to know about the X-rays is because that's what interacts with the sunlit side of our atmosphere. So we're totally protected. We cannot be harmed by an X-ray solar flare. Astronauts aren't really harmed by these X-ray flares because they're short in duration. They're generally quite impulsive, as we call it, lasting only minutes. But they do impact the sunlit side of our atmosphere. And that's why we care, because the ability to bounce radio signals off the atmosphere in a certain radio band that's still very commonly used, not only for emergency responders and or remote areas of the planet, but also for aviation, flying aircraft across the oceans. This is still a very common frequency band.
Okay, so solar flare we can associate with radio. Did you notice during the last eclipse, people had their glasses on and they were like, I see solar flares, but that's not right? That's not what they were looking at when they saw these bursts coming off the sun?
That's correct. Nobody saw any solar flare with those eclipse glasses. For one, there wasn't what's called the optical white light flare that happened during the eclipse. But the other is, it just wasn't possible. What they were seeing was sunspots, those dark regions on the sun that are an artifact of a strong magnetic field. And they're usually the source of most of the space weather storms that we receive here at Earth. And those were quite visible during the eclipse, some of these larger sunspot regions.
Okay. So are those the different or the same as geomagnetic storms?
Yeah, they're different. So the sunspots are active regions on the sun. They're areas where a strong magnetic field, if this is the surface of the sun where light escapes, has punctured through the surface of the sun. And that's what we reveal themselves when they're strong enough magnetic field. Think of it as a magnet sitting in the sun. Then a sunspot group forms. And it's not just as simple as a magnet. Sometimes these magnets begin to warp and twist and can even puncture through themselves. So you can get a very complex, stressed out area of magnetic field lines. And eventually, those tend to give and release that energy that's built up. And that's what can happen as a solar flare, along with other events such as solar radiation storms and the geomagnetic storms. The geomagnetic storm is what ultimately causes the northern lights and so many different impacts potentially to some of our technologies here.
Like what kind of technologies?
Well, the power grid, the ability for communications and GPS accuracy to take place, satellites in space can be a struggle to maintain their orbit during these storms because the atmosphere is so heated up. It's risen, it's become more dense. And satellites are what used to be, think of it like pushing your hand through the air and then pushing your hand through jello. This slows them down, and Earth's gravity begins to win the war and pull them back down, and will burn up in the atmosphere if that level isn't maintained in their orbit. So lots of these kinds of things are done during these events, and that's who we're talking to at SWPC. When I say SWPC, I'm saying Space Weather Prediction Center for short, SWPC. And that is who we're talking to make sure they get the information they need, know what's going on, and hopefully they can mitigate the problem.
Okay, so is a solar flare the same thing as a coronal mass ejection?
No, the solar flare is a burst of energy. Think of it as light, focused on X-ray, light emissions, speed of light stuff. We see it. The effect is already on the sunlit side of Earth. So there's no warning for it. We can only predict the probability that it will happen and how strong they may get to out over the course of 3 days. Before I get to the geomagnetic storm, then there's the solar radiation storms. Sounds scary, right? but that's particles coming from the sun. That's energized particles that we measure with some of the satellites in space to determine how many are coming. That's what can get into satellite components and cause actual anomalous behavior to the satellite. Can impact astronaut health on the space station or for the future missions. Aviators at high altitudes near the polar regions, they can become exposed to these highly energetic particles in their most extreme conditions or cases or numbers. And then you have so we have a little warning time there because it's particles. Even though they can get here almost speed of light, the fastest they can get here is about 15 minutes. So if we see the flare, the effect is on the sunlit side of Earth. It's already here. Then we have to think, will we see a radiation storm? Now we can think and put out a warning for the solar radiation storm if we think one's going to happen here at Earth. And then we think about a geomagnetic storm. Why? Because many of these are associated with something called a coronal mass ejection, or CME for short. That is an eruption of solar material in the form of plasma, as we call it, and a strong localized magnetic field stretching out into space. That's what we can put the whole gauntlet of watches and warnings out for and add to our forecast when we see these events. Because when they arrive, that's the energized particles I was talking about and the magnetic orientation, whether they can interact with Earth or not and produce the aurora, for example.
What's the warning time? Watch warning time.
For the radiation storms, it can be from minutes to hours. For a geomagnetic storm, it's usually anywhere on the order of 15 minutes to 45 minutes. The cool thing about a geomagnetic storm is when we see a CME leave the sun, we'll map it, we'll analyze it, we'll try to put it in one of our models that we have that helps us think about these, whether they'll arrive at Earth and how strong they might be when they get here. So we can put out a watch out to 3 days in advance. Then we wait. We wait. If nothing else happens, we wait. We wait for the CME to arrive at a satellite 1 million miles from Earth. So it's already made its 92 million mile journey. It only has 1 million more miles to go. Then we see it arrive at that satellite because that's measuring the solar wind out there. And we can clearly see it. Then we can think about putting out the warning, especially if it's a favorable CME, meaning it's going to magnetically connect with Earth. We can tell that at that time. And then we can fire out the warning. So usually that's about 15 to 45 minutes of lead time.
So if somebody's trying to plan a vacation to see the Northern Lights, are there times of year where this is more possible or less possible?
Yes, Emily, there sure is. During this time of year where we are, and I say time of year, meaning the time of the cycle, we are in solar cycle number 25. These are roughly 11-year cycles. And we're pretty much in and around the maximum of the cycle, meaning we're nearing or at the peak. That'll be determined later. But it's a slow come down. So already all of this year, all of next year, and even to 2026, as we start to come down from maximum, space weather storms are going to be more likely during this period because the magnetic fields are so stressed out. The sun is populated with sunspot groups and regions. As some of our posts have shown here of late, you've probably seen some of those yourself or your viewers and listeners. But don't forget about solar minimum. As we come down and the sun no longer has all these massive sunspot groups, there's a period of time where we come down from that increased chances for CMEs and solar flares and radiation storms, where you think they'd be quiet, but we get this giant feature called a coronal hole. And that alone can cause geomagnetic storms that result in the aurora being seen. And those are really quite predictable during that stage because they survive a solar rotation, which lasts 27 days. So if we had a good, say, a G1 or G2 storm on our 1 through 5 scale, 27 days later, it may happen again. So don't forget about that for planning purposes too, or you can look maybe a month or in advance and then book your trip to Iceland or wherever you want to go to maybe see the aurora.
Interesting. That's exactly what I want to do. So good call. Okay. Let's talk about misconceptions from your vantage point as an expert. What are some of the biggest misconceptions that you hear over and over again when it comes to space weather?
Yeah, one of them you already talked about. People get confused and don't quite understand the relationship between flares and radiation storms and CMEs. Space weather does not cause every problem that happens out there. More often than not, it's not space weather related. There was a major cell phone outage back in February of this year. It got blamed on solar flares at the time. That wasn't true. That did not impact that cell phone service in any way whatsoever. We had to actually message that and put that out there because we were getting calls about that. I think the best thing for people to do when they hear about space weather in the media or the press or on whatever it is that they're following, is to go to our webpage, swipsy.noaa.gov, the nation's official source for forecast space weather information, and see for yourself exactly what's happening. Because we'll usually put out, if we're expecting some kind of impact to our technology, we'll usually have something out there about that. And that's usually when we get into the 4 or the 5 levels on our scale, that becomes a possibility. I mean, it can happen at the lower levels, but normally the possibility increases as you get to that 4 and 5, the top ends of our scale.
Do you think in the way that weather here on Earth is like an ongoing work in progress when it comes to communication, that there's a good amount of work to be done when it comes to space weather communication as well, so that the public does understand a little bit more?
Oh, absolutely, Emily, no doubt. That's why I'm glad, and we love to cooperate and try to talk to the press and media whenever we can, because, we're all smart about terrestrial weather, right? It wasn't that necessarily that way 40 years ago when I was a younger man back then. I mean, people kind of knew what a tornado was, but now they really know what a tornado is. If you put out a tornado warning in the Weather Service, people know what that means. They have a visualization of it. They know this is a life or death situation. I need to take cover now. Space weather, they don't know what a CME is. They don't know what a flare is. So we have to spend a lot of time explaining that and then telling them what that actually means. So when you're doing shows like this, and that's something I in particular have been very involved with the press and media from last year through this year and even well into next year, of trying to get them not afraid to talk about space weather. Because if they're smarter about space weather, the audiences and the general public are going to become smarter about it. And then we not only become a weather-ready nation, we also become a space weather-ready nation.
We also could use like a Hollywood movie to make people really interested. I feel like Twister, even back the original one, made people really interested in weather. And then, of course, the second one as well. So, yeah, we need a good... Have you seen space weather like really poorly misrepresented in movies at all?
Oh, yeah. You see it with terrestrial weather as well.
Yeah.
It's just, it's one of those things. But it's glamorous, right? People don't understand it, so they can tend to think, oh, maybe this is a reality a little more so than what they know to be true with terrestrial weather. Because, the sun's a bit of a mystery to people. Space weather certainly is as well.
Yeah. Okay. I want to talk about what happened in May, because maybe if you're living under a rock, you just don't even know at all that there was an event in May and it was very successful, right? So can you take me through the process of forecasting that and then communicating the hazards and what you guys do at the Space Weather Prediction Center in order to kind of keep other entities safe during these events?
Sure, Emily. Thanks for that. This is great. This is a great opportunity to tell people what goes on behind the glory of the Aurora, because we came very close to having some impacts that would have affected people's lives in some areas of the world or this country in particular. But it didn't happen because it was successfully mitigated. And I'll get to that and end on that in a minute. So what happened? Well, it's solar maximum in and around, right? So the sun had some nice sunspot groups on it. 2 in particular were quite large back in early May. The one in the northern hemisphere of the sun was producing a lot of solar flares. But those solar flares were not providing radiation storms or even showing us any of these CMEs erupting from the sun. Surprisingly so, actually, because these were fairly strong flares, some of them. But that's space weather. However, a new region started forming and developing right in front of our eyes as a rotated into view. When I say rotated, the sun rotates on average every 27 days. So this other region started growing, developing the magnets that I talked about earlier, embedding and twisting and puncturing through each other. That really started to happen. We started messaging early in the week before the storms about this group, about the increasing likelihood of flares and other activity to follow. But that one started producing these CMEs. And when it did, it was rotated in kind of a direct line with Earth. So these CMEs erupted from the sun. It was fairly easy for us to determine that these were going to hit Earth. It was just a matter of when and how strong they might be. And it threw off CME after CME after CME. There was somewhere on the order of about 5 to 7 of these that were aimed, at least in some way, towards Earth. We put out, remember we have the 1 through 5 scale. We put out a G3 watch right in the middle of the range, about 36 hours before the CME arrived here at Earth. That got upgraded to a G4 watch. That's the top watch we put out. We don't do a G5 watch. That was done 24 hours before the storm arrived here at Earth. That's incredible. The last time we put out a G4 watch was in the year 2005. So that gives you an idea of the level of confidence and also how rare these events can be at that stronger, that most severe extreme level. So already our customers and critical infrastructure operators, the satellite community, the aviation community, the satellite communications industries, the GPS users, all these are already starting that subscribe and understand space weather already knew what this kind of meant for them, but so many don't, right? So the morning before the CME arrived, about 6 hours before it arrived at that satellite 1 million miles from Earth, there was still no sign of it yet. I decided that, hey, we probably better talk to one of our key infrastructure operators, which is the Power Grid of North America. So the whole southern provinces of Canada, through all 48 continental United States, they're all an interconnected power grid system. When we get to a 3 on our 1 through 5 scale, we're required to call them and let them know about a warning. And when we hit those levels, that's what we call an alert. In this case, we did something unique. So that gives them that 15 to 45 minutes of lead time for the warning. But this time they needed more. So I talked to our representative in the power grid and said, what do you think about doing this call now? And they said, that's a great idea. Please do it. So we did it. That call was allowed all these reliability coordinators, there's almost 20 of them throughout everything I just mentioned, that North American power grid, got on that phone call. I described what was going to happen, what we're expecting next, what this means. What's huge about that is that 6 hours, that allowed them to get giant transformers that would occupy the room I'm sitting in or more space, ready to go. Because what these storms do at that intensity, those severe and extreme levels, is they induce currents that don't belong there, the wrong type. We will live in an alternating current world, AC. This is direct current. That gets onto these lines and that can overheat transformers and damage them to the point of no repair where they have to get replaced. So when you get to this level of storm, what's going to happen is temperature alarms are going to go off as these transformers overheat. Voltage alarms are going to go off as the stability of the grid becomes unstable as they're trying to, do their magical work to maintain the integrity of the system and flowing at peak capacity. But what they were able to do with that lead time is get these things ready. So when the storm did arrive, and now we're calling them about the warning and then calling them about the alerts, they know exactly what's happening. They're seeing it on their systems 12, 15, 20 times stronger than what should be there normally. All these alarms are going off. In one case, they actually were able to switch over and use that other transformer. They couldn't have done that with 15 to 45 minutes, but they were able to do it with hours because they had it ready to go. That allowed the one that was overheating to cool down, and now the other one could spin up. They got high voltage transmission lines ready to ferry more electricity than normal or that weren't operational at the time ready, and they also switched over to that. And that's just the power grid. So for 24 hours plus, we were constantly engaged with the power grid of North America, and they were sweating it out, but they were mitigating the issue. Afterwards, talking to the Department of Energy and the power grid in another call, they told me two things that stick out in my head. Besides the thank you very much, this was critical information, it was great support. Two things stuck out in my mind. One was that if this storm had been too much stronger, they don't know if they would have been able to mitigate it successfully. The other was if there had been a major heat wave going on at the time, which there was not in early May, they don't know if they could have handled it successfully entirely as well, meaning there could have been some bulk transmission failures affecting hundreds of thousands of people with a power outage. So success story, but that's just one example of behind the scenes. Other industries that we're talking to, NASA, for the benefit of the astronauts on the space station, quite frequently throughout that period of time. We were talking to the satellite operators that are trying to maintain those orbits of those satellites and ones further out in space, giving them information. We were talking to the communication executives. I guess I won't name names for this, but all the big heads of the communication industry that we all rely on with our cell phones and cable services and such. We did a decision support call for them, provided the information so they stayed aware and they were informed totally what was going on in case there was a problem with their satellites or their comm systems. We talked to launch operators that were trying to send rockets off into space during that storm. Of course, they would not during certain periods of that event. And the aviation community, talking with air traffic control, controlling flights out over the oceanic regions. And they had to divert flights much further equatorward than usual so they could maintain the communications necessary because that geomagnetic storm was wiping out that ability in some cases. So there's a long answer to your question, but it's an important answer because I want people to understand that while they're enjoying the beauty of the aurora, this is what's going on for these types of events behind the scenes to maintain integrity and full operations of our systems.
Sean, this is like mind-blowing that all this is going on kind of without people realizing it too. And just like, do you ever feel overwhelmed with the amount of power that you have? It's crazy, like what you prevented and what you have the capability of preventing. Is that overwhelming?
It's inspiring is what it is. I mean, things I didn't even talk about. We're talking to FEMA. We've been doing a lot of work with FEMA over the last 20 years, the emergency response branch of our government. And they were prepared. They were ready for this now. They have plans in place. And ironically, we were involved in a tabletop exercise the 2 days before that storm arrived. It was a 2-day exercise. So the storm arrived Friday. I was deployed down to Denver to the FEMA Region 8 headquarters as their subject matter expert for space weather. My colleagues were in Washington, D.C. at the departmental head level of not only FEMA, but other government agencies for a tabletop exercise dealing with an extreme space weather storm. That one was much stronger in the scenario than what we experienced in early May. But let's put it this way. Thursday, day 2 of the exercise, we were doing in-person real-time briefing about the upcoming storm the next day. So FEMA could not have been more ready if there had been some major impact, such as a collapse of the power grid that affect hundreds of thousands of people, perhaps millions for days, if that were to unfold during that event.
What are some of these long-term, like life-threatening impacts of the power grid going down or satellites not being operable?
Yeah, it's critical, right? We take everything for granted. Our water system, that we turn on the faucet in our house, that relies on electricity and pressures that are worked with that. Think about the traffic lights. Those would not be functioning. Airports would be shutting down. I mean, the implications, refrigeration, right, would go down. And there's massive stores of refrigeration that the government has for emergency response. And we have so many catastrophic terrestrial weather events or man-made events these days. They have these to respond. Well, there's concerns about that going bad. So that even the recovery folks have to understand about space weather and the implications of what that means. So, the thing for people to take away today also, another thing, is that we are ready. I mean, that's not the benchmark event that we saw in early May. If you think of a G5, the top of our scale, as being, at the top of our heads, or a G5 that's 3 stories above our heads. What we experienced in early May was the one at the top of our head. The benchmark event that we know that we can happen, that happened in the year 1859, is that one that's 3 stories above my head, called the Carrington event. That's what the government's planning for. So the fact that we were able to, let's put it to kind of a test, how are we ready for the low scale G5? We proved that we're ready. Are we ready for that one 3 stories above my head? Well, we want to be, but we don't know if we're there yet. That's the concern. That's why this has survived. Space weather has survived every administration from since this really started becoming a thing back in the Obama administration through the Trump administration, who also emphasized certain aspects of this business to keep it going, all the way in through the Biden administration. So that's the good news, is that we are really ready, at least for these rare G5 events, and we want to be ready for that potential catastrophic one in the future.
I've heard some scientists say that we're overdue for that sort of event. What are your thoughts on that, or is that completely unpredictable?
Emily, I think that's fair. I think that's fair to say that we are overdue, because we are. I mean, 1859 was a long time ago. We did have a storm in 1989 that was maybe 1.5 times stronger than what we experienced in May, maybe not quite 2 times stronger. And that knocked out the electrical power in 2/3 of the province of Quebec, Canada. It damaged transformers severely in the northeast part of our country. There was a lot of irregularities and problems with the grid throughout the northern part of our country during that storm. And that was only 1.5 times, maybe even less stronger than what we experienced in early May. But we are overdue. That Carrington event, these are spewing off. We've already seen some, perhaps, even this cycle, but they were on the other side of the sun. We saw one in the year 2012, I think it was, that went sideways from the sun, not aimed at Earth. It was ahead of Earth's orbit. So fortunately, we didn't see it. But that's the one that we actually had an instrument over there at the time, a NASA research satellite. And it measured. So we know that was comparable with the Carrington level event. That could have been the one that's 3 stories above my head and arrived here at Earth. But for us here at Earth, yes, we are overdue for one to that level, but we did get one in May. It was historic. There's no doubt about it. The last time we hit a G5 at all was in the year 2003. And that storm was much more impactful than this one. And the one we had in May was probably stronger. Why was it less impactful? Because we're ready. There's been a lot of work done over the last 10 to 20 years around the world, global efforts. Not so much about strengthening the grid or strengthening satellites. Some of this just can't be done without enormous cost, but they're ready. They have plans. They have actions. We have support, decision support that we can provide. That's the difference. So what we can safely say that the storm in May was the most successfully mitigated extreme space weather storm in history.
Wow. Is there anything that individual citizens should or could do to prepare for such a thing?
Yeah, of course. I think the things that they do for terrestrial weather, have a generator for terrestrial weather events. If you're going to have that winter storm, it knocks off power for hours to a day or two. These events in space weather are very unlikely to ever cause us a major catastrophic issue, but we know it can happen. That's why we plan for it. So if you have these measures of weather radio, you have your non-perishable foods already stocked. Maybe these will come into play if we have a grid collapse. Also, know how to read a map. The old days of a fold-out map, because if we had one of these that knocks out power, let alone causes problems with GPS that we use, like, by the way, that did happen in May, with the storm in May affected a pretty substantial network of GPS users and their accuracy. But, if you're trying to navigate through a city and your GPS shows you so far off that you get confused on where actually you're at, well, then it's time to break out the map. And some of these storms can actually have that happen.
That's a very good point. I know younger generations that do not know how to read a map. So very important skill to have. Okay, you talked about space travel earlier, how the future of space travel is getting bigger. We're traveling more. We're going to the moon, Mars, maybe. So how does this all factor in, and what are the dangers here for astronauts in space?
Yeah, the dangers are significant. It's a risk that they're willing to take in the interest of exploration and science and just human discovery and proving what we can do. So that's great. But there's a risk there. And that risk really is more about the solar radiation storms, the one we haven't talked about so much. So, the astronauts on the space station, they're protected somewhat by the atmosphere, but not so much because they're pretty high up there. But they are in a low Earth orbit, so they still have some measure of protection there. But they're also protected by Earth's magnetic field, that magnetosphere, that magnetic barrier, protecting us from these injection of particles. That's why we don't get radiated through radiation storms. Even if you're on Mount Everest, it doesn't matter. The atmosphere and the magnetic field will protect us from these harmful particles. But as we go back to the moon, it's a problem because not only you're outside the atmosphere, you're outside the protective magnetic field of Earth. So they are got full exposure risk for these storms. So the only measure of protection they have, should one unfold on them, is their spacesuits, this thin fabric of metal material between them and outer space. And if they're on the moon, on the surface of the moon, doing a moonwalk and one of these unfolds, remember I told you these can get here in minutes, 15 minutes. So there's very little lead time here. But they have measures in place to try to do the best they can to protect those astronauts should they unfold. We're a big part of that. We are the support for those astronauts here at SWPC. When they go back to the space, we've already exercised that once during the mannequin mission out into space on that Orion capsule. And now when the 4 human beings are on there later next year going around the moon, we will have forecasters deployed to Houston Mission Control to directly support, kind of be the experts on site for the potential for these storms. And how damaging they can be to a human being? Well, let me give you a story. Back in the 70s, the last 2 missions to the moon, the Apollo missions. So you had Apollo 16 go up 3 months prior to one of these bad radiation storms. Apollo 17 went up 3 months after. So right in between, when nobody was out in space, we had one of the strongest in modern times in recorded history happen of these radiation storms. At the time, it was thought that it may have been lethal to astronauts in space. Now they think maybe not lethal, but just severe radiation sickness. Either way, it's a bad thing, right? Death is the worst, of course. But that's what we don't want to happen. We don't want these astronauts to suffer radiation exposure. So all they're going to be able to do is take measures. And they have some plans in place should one of these storms unfold. And then we're talking about space tourism, right? I mean, space launch is becoming a private enterprise. There will be human beings other than astronauts going into space. And they kind of maybe want to know about space weather for the protection of their human body, if that was to happen.
Do you think that, I mean, space weather prediction is like, I feel like a small group right now. Do you think it's just going to keep getting bigger and bigger and that there'll be private companies doing it too in the way that we do with weather here on Earth because we're expanding into space?
It's a true point, Emily. It actually is. There are businesses forming. One just formed recently. I can't think of the name. That has a heliophysicist, a space weather solar scientist in charge of it. And that's what they're doing is private support in the industry for space weather needs, specific needs for their customers, their customer base that will be. We do that in terrestrial weather. That happens too, right? There's enterprises out there that take the National Weather Service information or their own forecast, and they tailor it down to specific needs, like forecasting the temperature for men and women throwing down asphalt, to upgrade the roads. Those they can use our information in the Weather Service, but usually they want a specific temperature. They need to know the ins and outs of the asphalt and what that means. We don't do that. We can't get that fidelity in the Weather Service, but these private enterprises can. So yes, they are starting to grow and form when it comes to space weather. Some of the rocket industries, like there's many of them now that are sending rockets into space, and satellite companies are sending things into space. We don't know what all those, what their vulnerabilities are. So we can't track it all. So there's private enterprises forming to provide exclusive, specific support for their needs that they can trust and have a relationship with. Great, because we're it right now, and there's only so much we can do for them. But that is definitely something that's growing out there, just like in terrestrial weather. Yes, a few space weather enterprises showing up to give that super tailored, pay-for support.
Hopefully it'll be a good partnership like weather is.
Oh, yeah, it will be. We've got that really well in terrestrial weather. We're not a pay-for service in the Weather Service, right? It's taxpayers are funding this for their own safety and benefit. We all want to be able to get a weather warning for free, right? But if you want more tailored support that are really specific, that's where the paid, the private companies come into play.
Is there any talk of changing the scale ever? Because when you talk about G5 and then you're like, but this is here, and then the other one is 5 stories above, it seems like scale may not be the best indicator.
Yeah, I'm glad you brought that up, Emily. That's a really good point, because that's something that's actively been mandated to us, is to undergo an effort to seek and see if revision of the space weather scales is needed. Those were created decades ago, and the effects that they show on her, they're still applicable today, but they're not very descriptive as they could be. For instance, the flare talks about just HF radio blackouts, that high frequency, that specialized band from 3 to 30 megahertz. But we know that space weather can impact other communication bands, like happened on December 14th, an infamous day in the aviation community across this country, which if you want to ask me about when I'm finished answering this question, I'll be happy to answer that. Not that I want to scare them anymore, but just to know how space weather impacts their lives, and they never know about it or understand what was going on. But that is done by the Science of Technology and Policy Institute from our government. They've been mandated to lead that effort with our oversight. And we've been seeking input from all the users, from emergency management officials we've been very involved with over the last couple of years. Broadcast media folks have been part of that. Aviators, the power grid, all these industries have brought in, and the general public have been allowed to put in feedback about that. And in the end, whatever that report that comes from STIPI is, maybe it'll say, nope, you're better off keeping it the way it is, which we've seen feedback of that as well. And maybe there will be some kind of revision where we can get a better, accurate measure of things, a G5 at my head or a G5 3 stories up.
Has there been any talk of utilizing the wireless emergency alerts?
Yeah, a little bit. It kind of is in a way with what's called the NAWAS system. I can't think of what that stands for at the moment. It's what FEMA jumps onto and messages information, like that event in early May. Users are usually state watch centers and things like this, emergency centers that get that. But will there be a time where this gets fired out onto like the weather radio? It's quite probable, especially if we have one that is actually impacting stuff that's causing things to drop down or not work properly. Then that will become a critical part of messaging about the space weather storm itself.
What was the storm that you were going to tell me about?
Yeah, December 14th of 2023, we had an event happen on the sun that we don't normally talk about because it's not common. These happen routinely, don't get me wrong, but not at the level it happened in mid-December. So it's called a radio burst. Basically, the sun is a giant radio transmitter as well as everything else we talked about. And what happened on that day, on the sunlit side of Earth, which happened to be here in North America and South America, the sun let loose a significant burst of energy on radio frequencies that aircraft are using to talk to air traffic control across the domestic United States. It got so strong and so bad, it got to 10,000 times over the normal background level on that frequency on the sun. It happened to be right on those frequencies. What did that mean? Pilots looked like they were being jammed. They could not talk to air traffic control. Fortunately, these events last minutes, sometimes even shorter than minutes, but this one lasted up to 8 minutes. It got so bad in the northwest part of the country that they started tossing around the idea of shutting down airspace because the pilots and the air traffic control could not talk to each other on those line of sight frequencies above and beyond. So they're searching for frequencies that are garbled and they can actually make each other out. Fortunately, it was a good terrestrial weather day. Nobody was flying through low clouds and fog and everything. They could actually see and communicate via these other means. But that's how bad that event was. It was really frustrating from all the way from the East Coast through the Northwest United States. What made it so bad in mid-December is you have to have the sun in the background for it to be the jammer. If it's on the other side of the sky, you'd never notice an issue. Mid-December, near the winter solstice, sun's low in the sky, it's in the background, and it was in the background. So these planes were really having a difficult time. We called it unprecedented because we had never seen it that strong before. We thought it maybe be a once-time deal. Well, guess what? May 9th. Nothing to do with the CME that arrived on May 10th. The sun let loose another one of these that was probably stronger by the observatories that measure these. But this time, it took place when the sun was over the Atlantic Ocean where they're not using line of sight systems. But I do know the sun was up in Europe at the time, and I don't know the specifics yet, but it sounds like some elements in Europe were dramatically affected by that. I don't mean air traffic control, but there's military interests that we have and others. It sounds like there was some pretty significant impacts from that event, but aviation here was not impacted. So yeah, just another thing to understand and realize about the sun because these events impact things that people aren't even aware of.
Yeah. Was that worse at higher latitudes or was that just across the entire country?
In this case, it was just right where it really affected the United States because the sun was overhead in South America. We didn't hear of any impacts there because, anybody's talking air traffic control, the sun's overhead. It wasn't providing, just the flare was providing its normal HF problems on the sunlit side of Earth. But yeah, these events are extraordinary. And now the Federal Aviation Administration, the FAA, is extremely interested in radio bursts. So who knows, maybe we'll develop a new warning or alert out of SWTC here to help with those very rare events, but, critical. At the wrong time, if they happen, it can be really quite dramatic.
Just one more thing to make me scared of flying, so thanks for that. Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes published every Tuesday. If you have a friend that's interested in space weather, please share this episode with them. You can also now listen to the show on YouTube. Just search the National Weather Desk and find it under the podcast tab. Thank you so much to Sean Dahl from the Space Weather Prediction Center and to Garrett Hyde from Iowa News Now for joining me at the beginning of the episode. For the National Weather Desk, I'm meteorologist Emily Gracie. Make it a great day.